right, so we are going to continue using differentials. In this video, we're going to talk about some error ideas. So first, we just kind of have a couple definitions. Propagated error is basically error that results in certain maybe measurements like volume. If you have a reported error in one of its variables. So if you know an error in the radius, that will result in, there's a resulting or propagated error in the volume. So that's propagated or kind of this resulting error. Relative error and percent error, percent just in the percent form, relative in kind of a decimal form, is really an idea just that I talk about even in a gen ed math class. So it's just kind of the change in value divided by the original value. So if we think of the change in value as the change in the output value of a function, q, we're going to approximate that with the differential of q, the absolute value of that change in value. And then divided by whatever the original value of that function is when you sub in that original x sub 0. So let's take a look at an example. The diameter of a circular cylindrical tube is 12 inches, manufactured to be 12 inches, with a possible error of plus or minus 1/8 of an inch. We're going to use differentials to approximate or estimate the propagated error and the relative error in the area of the end of the tube. So the first thing we have to think about is just our formula for the area, because if my goal, so if I think about here that the propagated error that I want to think about in the area, so we're going to be using the differential to do that. So that's when we're thinking about we're going to need dA. The relative error, then we're going to be taking the absolute value of that dA divided by the A evaluated at whatever the initial value is here. It looks like we have a diameter of 12, so maybe with a radius then of 6. So those are the things that we want to do. We want to look at the propagated error, and then we want to look at the relative, and then we can think of it as a percent if we want to. So in order to find these things, so if these are then my goals are to find those two things, well, then I need area, right? So I need to think of my formula for area of a circle is pi r squared. This error that's given to us is the error in the diameter. So we have a couple of choices. We could maybe just take half of that and think about the error in the radius, or if we wanted to, we could just rewrite. Certainly the radius is equal to half of a diameter. I'm going to use capital D because later we use the differential lowercase d. So we have that if we want to just stick with the plus or minus 1/8, we can think of area as being 1/4 pi times the diameter squared. All right, so with that in play then, if we first want to start with what our propagated error estimate is going to be with our differential, then we are going to use our dA, so propagated error. dA is going to equal, bring down the 2, so we'd have a half pi times d, and then d, capital D, a little awkward there. So now if we were to find dA, we're going to have 1/2 pi times our diameter here is 12, and then times our error is this in the diameter, so the d, capital D, is the plus or minus 1/8. And so this is going to give us plus or minus, and then doing the 12 over 16 and reducing that to 3 over 4, we're going to have plus or minus 3/4 pi, and this is the propagated error using in the area, so using my units, this should be in terms of square inches. So this would be my estimate for the propagated error. So this is definitely what the differential is equal to. I would just say in general this is propagated error as estimated by our dA. Okay, so we'd estimate that the potential error then would be approximately plus or minus 3/4 pi square inches, the error in the area. All right, now let's go ahead and go on to find the relative or the percent. So let's do relative error here. So we'll do this for our relative error. Okay, so our relative error, so the relative error, again, as approximated with our differential, is going to be the absolute value of that dA that we just found, and then divided by the area with a radius of 6. So if this is subbing in my radius of 6. So my differential we just found to be the dA plus or minus 3/4 pi, and then divided by the area at the initial value here with a radius of 6 would just be 6 squared, so 36 pi. And so the absolute value then, so plus or minus is just going to then be our 3/4 pi. So we're just going to have our 3/4 pi divided by 36 pi, and then of course our pi's reduce, and then we're going to have the 3/4 times 1/36. So 1/12 there, so 1/48. So 1/48, which, give me a sec, okay, is our decimal. This is approximately 0.0208 if we round that. Okay, so this is our relative error, kind of in its decimal form here. So this is our relative error. Now, we're not asked for it here, but it might make more sense just to kind of end with thinking about then what is our estimate for the percent error using differentials is simply going to be taking that relative error and then putting it in a percent form. So our percent error would be approximately 2.08%. All right, so let's continue. Let's look at another example. This one is actually from your homework, and it should already be typed up in your notes. I didn't have it on the file I was using here, so I had to handwrite that out real quick before this video. All right, radius r of a spherical ball, is found by measuring the volume of the sphere. And so that's by a water displacement type of method is what they're referring to there. It's determined that the volume is 30 cubic centimeters with a tolerance of no more than 4%. So the tolerance in the volume. So basically what is being given right here is this is our percent error in the volume. So that's what that 0.04 is, or 4% is the percent, 0.04 is the relative. All right, so let's continue. We'll come back to that later. Use differentials to approximate the relative error and the corresponding percent error in measuring the radius. Okay, so what are my goals here as I kind of think about this one? So this time, as we think about what it is that we're using the differentials, so that's key here. So I'm using my differential. And the first thing is I'm going to be approximating the relative error here. So if I think about that, that means I'm going to want, and this is the error in the radius, my radius. So this is the absolute value of dr and then divided by r. So this is our goal, essentially. And then we're also going to want that as a percent formula as well. So kind of in its decimal, and then when we come down here, we'll say as a percent. Okay, so those are our goals. So that's what we want to kind of be thinking about here. All right, so if I want, think back to like what we did up above when we found the relative error, when we found dA over A. Okay, so when I found dA over A, that required, back up in the step in blue, I had to find dA. Well, how did I find dA? I needed the differential dA. That meant I needed some kind of formula for the area. So area as a function of the diameter, or I could have done it as a function of the radius. So what I need here to get started, so the first thing that I'm going to need is I'm going to need a formula for the radius, basically as a function of the volume. Okay, well, we can do that because if we know that volume is equal to 4/3 pi r cubed, so that's going to imply if you multiply by 3/4, so you'd have 3/4. Of course, you'd still have your v here. You could also divide by pi, so you could have 3/4 pi times your v is equal to your r cubed. And then if you go ahead and just think about taking your cube root of both sides, you now have r as a function of the volume. So here's what we have. R is going to equal, let's break off the constants just as this cube root of 3/4 pi. It's ugly, but it's just a constant. The variable is also under the cube root, but to differentiate it, let's think of it as v to the 1/3. All right, so here is r as a function of v. I think in some ways that is one of the harder parts of this problem, is just realizing it's not v as a function of r, I need r as a function of v because I want this dr and I'm given information about the error in v. Okay, so with that said, let's go ahead and find our dr. So dr is going to equal, so again, this cube root of 3/4 pi is just a constant multiple. And then we're going to bring down our 1/3. And then v to the 1/3 minus 1 would be our negative 2/3. And then dv. So there's my differential. Now, my goal, so we have a couple of choices. I mean, could I start to sub in, it looks like, we know the volume is 30, and, could I maybe start to sub that in? I don't have dv though. What I have, when I go back up here, what I then know is I have an estimate for what the absolute value of dv over v is, because I have that 4%. So it's dv is not 0.04, it's the dv over v that's the 0.04. And that's key. So I don't really have just dv. Hey, I have dv over v. Now, I have v, but what good's that going to do me here? So since my goal, this is another kind of tricky part of this problem, my goal was never to find just the propagated error, it was the relative error. So I really want, my goal was dr over r. So let's think about that. Let's go ahead and just say, all right, let's divide both sides here by r, because that is my goal. My goal is going to be this dr over r. Okay, now here's what we know. We know, okay, in my numerator, I still have this kind of ugly looking constant multiple here. So let's just recopy this. So cube root of 3/4 pi. And then now I have this 1/3, and I have the v to the negative 2/3, and I have my dv. In the denominator, I also know what r is equal to. Okay, r, back up here, if we think about what r was, I know r in terms of v. So I can write my r as cube root of 3/4 pi times v to the 1/3. Well, this looks kind of promising. Ugly radical constants can reduce, and I can also bring this v to the negative 2/3 down into the denominator, and it'll be a v to the positive 2/3. And when I multiply that by the v to the 1/3, that looks a whole lot nicer because that's just v. So here's what I now have. My dr over r is simply this 1/3 dv over v. This looks better because that's what I know something about is dv over v, remember? So here's what we now know. Okay, so what we now have, let's go down here. Then my absolute value of dr over r is going to be this 1/3 times the absolute value of dv over v. And so what we now have is this 1/3, and the dv over v, the absolute value of dv over v, that is simply our 0.04. And so we have 1/3 here times 4/100ths, which is what, 2/50ths or 1/25th, and that is our 1/75th, which as a decimal is 0.013 repeated. Okay, so this is our relative error as approximated by our differential, the absolute value of dr over r. Okay, so that then means that our percent error, so this implies that the percent error as estimated using our differential is this 1.3 repeated percent, or 1 1/3%, or if you prefer 4/3%. So any of those, but that is our percent error as estimated with the differential. So kind of interesting here, I actually never needed to sub in that 30. So a little bit of the actual volume, a little bit of extraneous information that I didn't have to use here. All right, last little piece here. So what does that mean about the actual radius? Well, the actual radius then, whatever, so let's think about what that might look like. So my actual radius, r, would have this error of this 1/75th. So it could be minus 1/75th times r, or it could be as an error. So error kind of implies it can go in either direction, right? So, or it could be plus 1/75th r. So it could be as low as 74/75ths of the r, or it could be as high as 76/75ths of that r. All right, so we will stop. That was kind of definitely a little bit harder of a one there. When we come back next time, we're going to talk about Newton's method.